Künstliche Intelligenz soll, so die Botschaft dieses Textes, ein Leuchtfeuer für militärische Modernisierung sein, und nicht eine Flamme, die am Ende alles verbrennt. Der Autor warnt, je stärker KI in Aufklärung, Analyse, Führung und Waffensysteme eingebaut wird, desto gefährlicher werden versteckte Schwächen, wenn man sie ignoriert. Entscheidend sei deshalb, dass am Ende immer der Mensch die letzte Kontrolle behält und dass Algorithmen unterstützen, statt Verantwortung zu ersetzen. Im Kern beschreibt der Beitrag 6 große Problemfelder, die wie ein schleichender Schaden wirken können. Erstens, tief verankerte Verzerrungen und Vorurteile. Wenn eine KI vorhandene Ungleichheiten übernimmt, kann das im Militär nicht nur den Zusammenhalt schwächen, sondern auch fatale Fehlentscheidungen begünstigen, mit ethischen Folgen und einem Vertrauensverlust in die Legitimität von Einsätzen. Zweitens, erfundene oder falsch dargestellte Fakten. Wenn Informationen verzerrt sind, entstehen falsche Lagebilder, daraus werden Fehlentscheidungen, daraus können Kollateralschäden entstehen, bis hin zu operativen Niederlagen. Drittens, Zielkonflikte und falsch gesetzte Zielvorgaben. Wenn die KI auf ein Ziel optimiert, das nicht sauber definiert ist, kann sie zwar effizient wirken, aber das eigentliche, rechtlich und ethisch vertretbare Ziel verfehlen. Viertens, Datenvergiftung. Wenn Gegner Trainingsdaten manipulieren oder Eingaben gezielt verfälschen, kann ein scheinbar stabiles System plötzlich kippen und unzuverlässig werden. Fünftens, Überanpassung. Eine KI kann in Tests glänzen, aber im echten Chaos versagen. Bei anderem Wetter, schwierigem Gelände, Nebel, Staub, Störungen, Täuschung. Und sechstens, der Blackbox-Effekt. Wenn niemand nachvollziehen kann, warum die KI etwas empfiehlt, entsteht Misstrauen. Und die Zusammenarbeit zwischen Mensch und Maschine wird brüchig. Die Warnung dahinter ist klar. Wird diese Mischung aus Bias, Falschinformationen, Manipulation und Intransparenz in militärische Systeme eingebaut, kann das nicht nur einzelne Einsätze gefährden, sondern eine Kettenreaktion auslösen, die die Ethik des Krieges und die Sicherheitslage insgesamt verändert. Deshalb, sagt der Autor, müsse man nicht nur fragen, was KI leisten kann, sondern was sie mit sich bringt und wofür wir sie am Ende nutzen wollen. Als Antwort fordert der Text ein Frühwarn- und Präventionssystem. Technisch heißt das, erklärbare KI, damit Entscheidungen nachvollziehbarer werden. Saubere Datengovernance, damit Trainingsdaten echt, korrekt, sicher und verlässlich sind. Mehr Robustheit durch Tests gegen Angriffe und gegen Täuschung, inklusive strenger Prüf- und Bereinigungsprozesse, damit Gift nicht ins System gelangt. Und organisatorisch und politisch. Das Prinzip der sinnvollen menschlichen Kontrolle, also dass kritische Entscheidungen letztlich von Menschen verantwortet werden. Dazu gehören ethische Bewertungen, klare rechtliche Leitplanken für autonome Waffensysteme, laufende Überwachung der Systeme und verbindliche Regeln für den militärischen Einsatz von KI. Am Ende steht ein Satz, der wie ein Warnschild wirkt. KI darf ein Werkzeug der Transformation sein, aber sie darf nie die Verantwortung übernehmen. Denn es geht nicht nur um nationale Sicherheit. Es geht darum, ob wir in einer technologischen Revolution unsere Grundprinzipien behalten.
And he also did tours at, I think, SET Corp, Psy Corp, Vulcan Park, right? So it's actually a great honor to have him here today. And without further ado, I think he will give us an introduction or a status of Explainable AI. So thanks, Dave.
Very good. Great. Yeah, thanks, Oliver. That was a pretty nice introduction. That glass of wine I bought you paid off, I think. That might be it. So I'm going to tell you about this Explainable AI program I'm running now at DARPA, which we started. It's about halfway through. It's a 4-year program. We're just about halfway through, so I can give you some kind of report on things people are trying and where we are, although, it's an ambitious effort. As you can imagine, DARPA now has a huge emphasis on AI, but also has a big emphasis on using AI for human-machine symbiosis. So that's how XAI was created. They really, are trying to see how can AI be best used as a partner for knowledge workers, people in the services, and that sort of thing. And if you don't know, program managers at DARPA come for just a 4-year tour. It's the way they keep things fresh, is they don't let people come there and stay forever. So they're constantly refreshing with new people and new ideas. So actually, if you're at the right point in your career, you think you could spend 4 years in Arlington, Virginia, and you're interested in AI and human-machine symbiosis, let us know. That it's a great job if you don't mind living on the East Coast, and you really get to do some interesting work. So with that, let me talk a little bit about XAI. Here, everybody now knows the motivation for the program, right? When we started it 3 years ago, it wasn't always clear. People would ask, why do you need to explain these systems, right? And seemed to be endlessly fascinating to the press that AI needed to be explained, right? So it seems like one of the most influential things I did was created the acronym XAI. I think that's where the X first came from. So now I can retire having had that influence on the community. But the need is, we've had this explosion of machine learning, AI systems, especially deep learning now, being applied everywhere. But these models are opaque and difficult for users to understand. In a lot of cases, that's okay. It doesn't matter. If you're finding cat videos on Facebook, I'm not sure that, it's critical to get an explanation. But certainly if you're in the Defense Department or finance or medicine, right, these explanations become a lot more important. And one of our lead researchers, actually, now he's been working on the program for one of our principal investigators for 2 years. He had an amazing anecdote. His experience with unexplainable AI was he went into the doctor for his annual physical. And a week later, of course, the nurse calls him up with the results and goes through his numbers, which seemed to be okay. And then she said, have you heard of algorithms? And he said, well, yes, I've worked with algorithms. I know about that. Well, our algorithm says you should start taking statins. And his cholesterol was not high. So he's like, why? Why? And she says, well, we don't know. That's what the algorithm recommended. And he said, well, what's the algorithm based on? She says, well, age and gender mostly. And he said, well, do you always recommend statins for everybody that's a male my age? And she said, no, only if the algorithm recommends it. And said, we get a number out of the algorithm, and yours was 12.5, and if anything over a 9, we recommend you take statins. And then he went through a whole dialogue he was on high blood pressure medicine. He just stopped that, and they took out the blood pressure out of his profile, and the number dropped to 9.5, but was still high enough that he should take them. So I think in the end, he just decided to just take them to be safe, but it was always kind of a mystery exactly why the algorithm had recommended that. So that's the kind of story you hear a lot of these days, right? There's a lot of people using these systems, and a lot of people won't use the systems if they don't have some explanation, right? That's, for reasons like that. So that's our goal, is to try to do something to this technology to make it more understandable to the end user. Here's how I characterize, the standard supervised machine learning process today, which is, the basis of this technology that's being applied everywhere. You have a lot of training data, generally a lot of labeled training data. You feed that to a learning process. You then get a learned function or a model. And there's a variety of these, although, of course, deep learning is the one that's really paid off, that's really in vogue today. You can get a very large, complicated model. And unlike this simplified one I have here, with 5 or 6 layers, they can have thousands of layers, millions of nodes or neurons, right? And each one is learning concepts in a way by the weights and the equations that it learns at each node. So it does a pretty good job of prediction, but the system really has no idea how to describe the concepts that it's using. So in this simple example, now we've trained this system to recognize objects. We feed it this photo, and sure enough, it says, this is a cat. But if you want an explanation on why do you think it's a cat, much like my friend at the doctor, it says, well, the weight on the cat node is 0.93, and that's about all you'll get out of it. And so that leaves the user, if he cares, wanting to know, why did you make that recommendation? Why not something else? Even more importantly, what are your strengths and weaknesses? When should I trust you? When shouldn't I trust you? That's one of our real goals of the program, is to help the user have appropriate trust and know when he can depend on the system and when not. Well, that's a very It's a very ambitious goal, but that's what we're trying to get at. So here's how we're changing, the broad strategy for what we want to do to help this situation is to change this process in two ways. One is have a modified machine learning process, so that it produces something that's more explainable, right? It extracts out some features, can identify training examples, there's a variety of ways, which I'll show you the program and several of the people that presented papers yesterday are working on how can you make these systems a little bit more explainable, pull some semantic features out of the net, make the net more structured, maybe use a different learning technique produces a more structured model. So there's a variety of techniques people can try. And then the second is to add the right human-computer interaction to it so you can create this explanation interface that takes the features or the ideas, the concepts that come out of the explainable model and translate that into an understandable dialogue for the end user. And our target here is the end user who's probably an expert in his domain. He's using this decision tool, but he's not an expert in machine learning or statistics. So you're trying to explain to him what are the important features or ideas or examples this system is using to make that decision. So here's how I've characterized the overall goal of the program. To start with, I think there's this notional graph. I think there is some inherent trade-off between the competency or the learning performance of the AI system and how explainable it is, right? The most complex deep learning system is going to be inherently more difficult to explain than a decision tree or logistics regression, and that's what I mean by these orange dots on the curve. Much like people, you can have ones that are completely brilliant but unable to explain anything to a normal person, or you can have people that make great instructors even though they're not the most recognized researcher in the field. So you have something like that going on with machine learning techniques. So I don't believe we're going to create something out in this corner. We're not going to have perfect explanations for the most complex deep learning system, but the goal of the program is to create a portfolio of techniques so we move this curve up and to the right. So a future developer can look at the trade-off between learning performance and explainability for new application, and he'll have better techniques to use to do a better job of satisfying that trade-off for his particular application. So for the program, we're using these two kind of motivating use cases or challenge problems. They're clearly designed to be relevant to the Department of Defense that DARPA cares about, but also clearly apply to all sorts of commercial, and civilian applications. So one is data analytics, especially on multimedia data, right? So we, have analysts in the government who pore over huge volumes of images and video, from North Korea or Syria or whatever, where it's critical that they get automated help to help them sift through all that information. But when they get a recommendation from the system that, oh, this is something you should look into, that analyst wants some explanation on why. And actually, before the program began, I was at a workshop with some government analysts, and one of the analysts there, and this was a bunch of machine learning people trying to pitch their technology to this analyst, and she said, well, this doesn't address my problem. Said, I already have these big data analytics routines that are giving me recommendations, but I have to put my name on the recommendation that goes forward, and if it's wrong, she's blamed, not the algorithm, and so she's very reluctant to use these algorithms unless she had some idea why it was making the decision. So that's one use case. Of course, that's just the same as the use case you might have for medicine or finance or other cases where you've got a lot of data, you're training the system to make classifications, now you want to know why it's made those decisions. The second use case is a little bit further out, but it's for autonomy, right? So we now have autonomous systems now like self-driving cars that are out there being developed still. And for the most part, they're still carefully engineered in a lot of software modules where you get some explainability out of it. But the most advanced researchers are now applying deep reinforcement learning to train these systems to have a decision policy. Much like what DeepMind did with AlphaGo, right? So that technique will be retraining robotic systems and autonomous systems in the future. And when that happens, an operator may send one of these systems off on a mission, like one of these military cases, sending off a UAV to do surveillance. And if it comes back, he'll want to know, why did you make the decisions you did? Why did you turn around? Why did you or didn't find, the target, right? So that's the goal of the second use case. In the program, we're only looking at simulated autonomy, often in video games or some simulated environment. But we want to see, if you have a system that's been trained with this deep learning technology, how can you pull out explainable decision policies out of that? So here's how we've structured the program. As I said, it began 2 years ago. As DARPA does business, we issued a solicitation. We got in a huge number of fantastic proposals. It was very timely, topic of strong interest to the research community. And we have these 11 teams in the list here that are all trying different techniques to provide both of these components, to both have a new learning process that produces a more explainable model, and to have the right explanation interface so that can explain its decisions to an end user. Have 3 teams that are working on both of those challenge problems, analytics and autonomy. 3 teams working only on autonomy, 5 teams working only on analytics. I have one other 12th team up here in the corner, IHMC, who's just a group of cognitive psychologists who are there not to develop a system, but just to dig through all the literature on the psychology of explanation. And there's a lot of this in education and decision making. When is one explanation better than another? When does an explanation contribute to a decision? When does an explanation engender trust? So they're there to just try to dig out the nuggets from all of that psychological literature and make it available to the rest of the team. So I've got, like I say, got a variety of techniques being applied. Several people, going after deep learning in particular, but have other people trying different techniques. This group at Dallas is using tractable probabilistic logical models. It's kind of a variation of Markov logic nets, where if you can train the system, you end up with a very structured result that you can actually do reasoning with. It's not as opaque as a deep learning system. Have other teams like Charles River and Rutgers in particular, who are trying to do something that's model agnostic. They're not trying to open up the black box and understand what's happening inside of it, but they can experiment with it and see if somehow they can infer a model that explains the decisions the system is making. So we've got this variety of techniques, and basically for the rest of the talk, I'm going to give you some examples of different techniques these people are trying, first both for the explainable model. Then we have done just the first round of initial evaluations, show you just samples of some of the data we're getting out of these experiments.